No effort required, just listen, and let the ancient world do the rest. There is a question that every human being who has ever lived has felt, even if they never put it into words. What if I could go back? What if I could return to a moment that has passed? Correct a mistake. See someone again. Witness an event that happened before I was born. Stand in a world that no longer exists and breathe its air and hear its sounds. Or go forward, into the future, beyond death, beyond the limits of a single human life, to see what the world becomes. Time travel is the oldest dream of the human imagination. It appears in the mythology of ancient India, in the folklore of Japan, in the stories of the Bible and the Quran, and in the 20th century, for the first time in human history, it stopped being merely a dream. It became a scientific question, a question that the greatest minds in physics have grappled with for over 100 years, a question that has produced some of the most extraordinary and counterintuitive discoveries in the history of human thought, a question that is still not fully answered. Tonight we explore it, gently, carefully, from the very beginning. What is time? Can it be traveled? And what does science, real science, not science fiction, actually say about the possibility? Let the question carry you and rest. Before we can ask whether time travel is possible, we must ask something more fundamental. What is time? It seems like a simple question. You feel time passing right now. You experienced it this morning when you woke up. You will experience it tomorrow. Time is the most intimate and immediate feature of human existence. And yet, when the greatest philosophers and scientists in history have tried to define it precisely, they have found themselves in difficulty. Saint Augustine of Hippo, the great theologian and philosopher of the 4th century, wrote one of the most honest statements ever made about time. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. Saint Augustine, Confessions, 397 CE. What then is time? If no one asks me, I know what it is. If I wish to explain it to him who asks, I do not know. 1400 years after Augustine wrote those words, physicists are still grappling with the same problem. The ancient Greeks thought of time as cyclical, repeating like the seasons. History was not a line moving forward, but a wheel turning endlessly. The same events would recur. The same civilizations rise and fall. Newton, the great mathematician and physicist of the 17th century, thought of time as absolute, a river flowing at a constant rate through the universe. The same for everyone everywhere, immovable, unchangeable, background. Time was the stage on which the universe performed, and the stage did not participate in the performance. This was the understanding of time that dominated physics for 200 years. Comfortable, intuitive, matching everything we experience in daily life. It was completely wrong. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that dismantled Newton's understanding of time so completely that physics has never fully recovered its footing. His name was Albert Einstein, and what he showed, with nothing more than thought and mathematics, was that time is not a river flowing at a constant rate for everyone. Time is more like an ocean. It bends, it stretches, it flows faster in some places and slower in others. It is affected by speed. It is affected by gravity. It is not a background against which events occur. It is part of the fabric of the universe itself. And if time is part of the fabric of the universe, then perhaps, like any fabric, it can be folded, stretched, torn. Perhaps it can be traveled. Newton's absolute time dominated physics for 2 centuries. Einstein destroyed it in a single paper. But what Einstein replaced it with was not simpler or more comfortable. It was stranger, more beautiful, and it opened the door to possibilities that Newton could not have imagined. In 1905, Einstein published his special theory of relativity. The central insight of this paper was deceptively simple in its statement and devastating in its implications. The speed of light is the same for all observers, regardless of how fast they are moving. This sounds unremarkable until you think about what it means. Imagine you are standing still and you throw a ball forward at 10 kilometers per hour. To you, the ball moves at 10 kilometers per hour. To someone running toward you at 5 kilometers per hour, the ball appears to move at 15 kilometers per hour. Speed adds up. This is the intuitive Newtonian understanding of how speeds work. Now imagine instead of a ball, you shine a beam of light. Light travels at approximately 300,000 kilometers per second. If you shine that light while standing still, it travels at 300,000 kilometers per second. But if you shine it while moving towards someone at half the speed of light, how fast does the light appear to move to them? Intuition says faster. 300,000 plus half of 300,000. The answer is exactly 300,000 kilometers per second. The same. Light speed does not add up. It is a constant, an absolute limit. The speed of light is the same for everyone regardless of how fast they are moving. This single fact, experimentally verified, mathematically necessary, physically real, has consequences that shatter every intuitive assumption about the nature of time. Because if the speed of light must remain constant for all observers, then something else must change to make that possible. And that something else is time itself. Time must slow down for fast-moving objects so that light speed remains constant for everyone. Einstein's special theory of relativity showed that time is not universal. Two observers moving at different speeds will measure time passing at different rates. The faster you move, the slower time passes for you relative to a stationary observer. This is not a trick of measurement or perception. It is a physical reality of the universe. Time slows down for fast-moving objects. This is not science fiction. This is not speculation. This is one of the most thoroughly tested and verified predictions in the history of science. Every particle accelerator on Earth confirms it daily. Every GPS satellite in orbit depends on corrections for it to function accurately. Every experiment ever designed to test it has found it to be exactly, precisely, measurably true. Time passes at different rates for different observers. Newton was wrong. Time is not absolute. And if time is not absolute, then the question of whether it can be traveled suddenly becomes not a fantasy, but a physics problem. Einstein showed that time slows for fast-moving objects. But this was not merely a theoretical prediction. It has been measured, confirmed, used in technology we depend on every day. The slowing of time is real. And that means something extraordinary. Time travel to the future is not only possible, it is already happening. In 1971, physicists Joseph Haffel and Richard Keating placed extremely precise atomic clocks on board commercial airliners flying around the world. The clocks flew. The physicists waited on the ground. When the planes landed and the clocks were compared, the airborne clocks showed a different time than the ground clocks, by a tiny but measurable and precisely predicted amount. The clocks on the plane had experienced time differently than the clocks on the ground. This was not a malfunction. This was not an error. This was time dilation, the slowing of time for fast-moving objects predicted by Einstein's relativity, measured directly with real clocks on real aircraft. The Haffel-Keating experiment was one of the most direct confirmations of relativistic time dilation ever performed, and it has been repeated and refined many times since with increasing precision and always the same result. Time passes more slowly for moving objects. The effect at aircraft speeds is tiny, fractions of a microsecond, but the physics that produces it is the same physics that would produce dramatic time dilation at speeds approaching the speed of light. The GPS satellites orbiting Earth at 14,000 kilometers per hour experience time dilation due to their speed. They also experience a different gravitational time dilation because they are far from Earth's mass. Without corrections for both effects, derived directly from Einstein's relativity, GPS systems would accumulate errors of approximately 11 kilometers per day. Your phone's GPS works because Einstein was right about time. Your phone's GPS works because Einstein was right about time. Every time you navigate somewhere using your phone, you are using technology that depends on the fact that time passes at different rates in different conditions. Einstein's relativity is not an abstract theory. It is embedded in the infrastructure of daily life. Now, consider what happens when we scale this effect up. At 10% of the speed of light, time slows by about 0.5%. Small, but measurable. At 90% of the speed of light, time slows to less than half its normal rate. A year on a fast spacecraft would be less than 6 months experienced by the traveler. At 99% of the speed of light, time slows to about 1/7 of normal. 7 years passing on Earth while the traveler experiences 1. At 99.99% of the speed of light, time slows to less than 1/100th of normal. A traveler moving at near light speed for what feels to them like a single year could return to Earth to find that decades or centuries have passed. This is time travel to the future, not science fiction, physics. Time travel to the future is physically real. The faster you move, the further forward in time you travel, relative to those left behind. But what about the other direction? What about the past? This is where the science becomes stranger, more controversial, and more deeply fascinating. Because the same physics that enables forward time travel raises the question of whether backward time travel is possible. And the answer involves one of the most extraordinary objects ever theorized in the history of science. In 1935, Albert Einstein and his colleague Nathan Rosen published a paper describing something remarkable: a solution to Einstein's equations of general relativity that described a bridge. Not a physical bridge made of stone or steel, a bridge in the fabric of space-time itself. A tunnel connecting two different points in the universe, or potentially two different points in time, through a shortcut that bypassed the ordinary geometry of space. Einstein and Rosen called it a bridge. Physics now calls it a wormhole. Imagine space-time as a sheet of paper. Point A is at the top of the sheet. Point B is at the bottom. If you want to travel from A to B along the surface of the paper, you must traverse the entire length of the sheet. But if you fold the paper, bringing A and B close together in a higher dimension, you can punch a hole through both layers and create a tunnel, a direct connection, a shortcut that bypasses the distance entirely. A wormhole does this to space-time. It folds the fabric of the universe and connects two points that would otherwise be separated by vast distances, or vast spans of time. The mathematics of Einstein's general theory of relativity permits the existence of wormholes. They are not forbidden by the known laws of physics. However, all currently theorized wormholes would be extraordinarily unstable, collapsing almost instantaneously. To hold a wormhole open long enough for anything to pass through would require a form of matter with negative energy density, so-called exotic matter, which has never been observed in macroscopic quantities, though quantum mechanics suggests it may exist at the smallest scales. Exotic matter, matter with negative energy, matter that pushes outward instead of pulling inward, matter that would hold the throat of a wormhole open against the tendency of gravity to collapse it. Physicists Stephen Hawking and Kip Thorne, two of the greatest theoretical physicists of the 20th century, spent decades debating whether wormholes could exist stably and whether they could be used for time travel. Thorne showed that a wormhole, if it could be held open, could in principle be used not just for space travel, but for time travel. If one mouth of a wormhole were accelerated to near light speed and then brought back, the time dilation effect would create a time difference between the two mouths. Step into one mouth and emerge from the other at a different point in time. A wormhole as a time machine. The mathematics works. The engineering is another matter entirely. We have never observed a wormhole. We have never created exotic matter in macroscopic quantities. We have no technology remotely capable of manipulating space-time geometry on any scale. But the universe has never told us it is impossible. And in physics, that matters. The mathematics of wormholes allows for the possibility of time travel. The physics does not forbid it. But as we push further into the question of backward time travel, deeper complications arise. Complications that have troubled physicists for decades. Because if you could travel to the past, certain things would seem to follow. And those things appear to be logically impossible. The most famous problem with backward time travel has a name: the grandfather paradox. It goes like this. Imagine you build a time machine and travel back to the time before your grandfather met your grandmother. And imagine, for whatever reason, that you prevent them from meeting. They never have children. Your parent is never born. You are never born. But if you are never born, you cannot travel back in time. You cannot prevent your grandparents from meeting. So they do meet. Your parent is born. You are born. You travel back in time. You prevent them from meeting. And around it goes. A loop with no beginning and no end. A cause that eliminates its own effect. An effect that eliminates its own cause. The grandfather paradox suggests that backward time travel is logically impossible. That any attempt to change the past creates a contradiction that the universe cannot resolve. Physicists have proposed several responses to this paradox. The first is the Novikov self-consistency principle, named after the Russian astrophysicist Igor Novikov. The Novikov self-consistency principle proposes that any event that occurs as a result of time travel must be consistent with the original history. You cannot change the past because anything you do in the past has always been part of the timeline. If you travel back to the time of your grandfather, you will find that it is impossible, through any means, to actually prevent him from meeting your grandmother. Not because of a physical barrier, but because of a deeper logical consistency built into the structure of time itself. You cannot change the past because the past has already happened. Whatever you do when you get there, you already did it. History already contains your actions. Time is self-consistent. The second response is the many worlds interpretation, drawn from quantum mechanics. When you travel to the past and make a change, you do not alter your original timeline. You create a branch, a parallel universe. Your grandfather is not prevented from meeting your grandmother in your original timeline, only in the new branch that your intervention created. You cannot return to the universe you came from, but you have not created a paradox. You have created a new world. The third response is the one that Stephen Hawking preferred. He called it the chronology protection conjecture. The universe, through mechanisms we do not yet fully understand, prevents the formation of time machines, not because they are logically impossible, but because something in the deep structure of physics makes their creation physically impossible. The universe protects its own history. Whether Hawking was right, nobody knows. The paradoxes of backward time travel push against the boundaries of logic itself. But there is a deeper puzzle beneath all of these paradoxes. A puzzle that the paradoxes are actually symptoms of. Why does time have a direction at all? Why does it flow forward? Why can we remember the past but not the future? Why is there an arrow of time? And the answer to this question may hold the deepest clue to whether time travel is ultimately possible. Here is something extraordinary. Almost every fundamental law of physics works equally well in both directions of time. The equations of classical mechanics, the equations of electromagnetism, the equations of quantum mechanics. Run them forward and they describe the world we know. Run them backward and they still work. The mathematics does not know which direction time is flowing, and yet time clearly flows in one direction. You watch a glass fall from a table and shatter on the floor. You have never watched the shards of a broken glass spontaneously reassemble themselves and leap back onto the table. The forward film and the backward film look completely different. One is the world we know. The other is absurd. Why? If the fundamental laws are symmetric in time, why is our experience of time so overwhelmingly asymmetric? Why does time have an arrow? The best answer physics has found comes from thermodynamics, from a concept called entropy. Entropy is a measure of disorder in a system. The second law of thermodynamics states that in any closed system, entropy tends to increase over time. Order becomes disorder, hot things cool, ice melts, coffee cools. Broken glasses do not reassemble. The arrow of time, the reason we experience time as flowing from past to future, is the arrow of increasing entropy. Time flows in the direction that entropy increases. The reason the glass does not reassemble is not that physics forbids it. It is that the number of possible configurations of shattered glass is vastly larger than the number of configurations of an intact glass. Moving from order to disorder is overwhelmingly more probable than moving from disorder to order. Time flows in the direction of increasing disorder because disorder is overwhelmingly more likely than order. But this answer, elegant as it is, raises a deeper question. Why was the universe in a state of such extraordinary low entropy at the beginning? Why did it start ordered? If entropy was already high at the beginning, there would be no arrow of time, no direction for it to flow, no past and future, no time as we experience it. The arrow of time may ultimately be a consequence of the initial conditions of the Big Bang, of why the universe began in such an improbably ordered state. And why it did is one of the deepest unsolved problems in all of physics. Time flows forward because the universe began in a condition of extraordinary, improbable order, and we do not know why. The arrow of time points forward because entropy increases. The universe began in an improbably ordered state, and time flows from that ordered beginning toward an ever more disordered future. But what does modern physics, the physics of the 21st century, with its quantum field theories and its string theories and its deepest investigations into the nature of reality, actually say about the possibility of time travel? We are closer to an answer than we have ever been. And the answer is more nuanced than either yes or no. Where does physics stand today on the question of time travel? The honest answer is closer than ever to understanding the question, and still far from a definitive answer. Time travel to the future is confirmed. It happens. It is measurable. The faster you move, the more slowly time passes for you relative to the rest of the universe. In principle, given a spacecraft capable of accelerating to near light speed, a traveler could leave Earth today and return hundreds or thousands of years in the future, while experiencing only years or decades themselves. The technology does not exist. The physics is settled. Backward time travel is more contested. The mathematics of general relativity permits it under certain conditions. Wormholes, rotating black holes, certain exotic space-time configurations. The mathematics of quantum mechanics introduces additional complications and possibilities that physicists are still working through. Stephen Hawking spent much of his career believing that backward time travel was impossible, that some physical mechanism would always prevent the formation of time machines. His chronology protection conjecture was his attempt to formalize this intuition. But Hawking himself acknowledged that he could not prove it. In quantum mechanics, there is a phenomenon called quantum entanglement, in which two particles can be correlated in ways that appear to transmit information instantaneously across any distance. Some physicists have explored whether quantum mechanics might allow for a form of information transmission backward through time. The results are mathematically subtle and experimentally ambiguous. No definitive demonstration of backward causation has been achieved, but the possibility has not been definitively ruled out. The question of backward time travel touches on the deepest unsolved problems in theoretical physics. The relationship between quantum mechanics and general relativity, the two great pillars of 20th century physics that have never been fully reconciled with each other, is perhaps the central problem of 21st century physics, and time sits at the heart of that reconciliation. What is time at the quantum level? Does it have the same character as time in relativity? Does it even exist as a fundamental feature of the universe? Or does it emerge from something deeper? Some physicists have proposed that time is not fundamental at all, that it is emergent, that at the deepest level of reality, at the level of quantum gravity and the Planck scale, there is no time. Only a deeper structure from which time, as we experience it, arises. If time is not fundamental, then the question of whether it can be traveled takes on an entirely different character. Not can we move through time, but what is time, really? And we do not yet know. Modern physics has confirmed time dilation. It permits wormholes mathematically. It has not definitively closed the door on backward time travel, and it has discovered that time itself may not be what we think it is. All of this brings us to the final question. Not can we travel through time, but what does our deep uncertainty about time tell us about the nature of the universe and our place in it? We began with a question that every human being has felt. What if I could go back? Science has not answered that question completely. It may never answer it completely. The nature of time, whether it is fundamental or emergent, whether its arrow is necessary or contingent, whether its geometry permits backward travel, remains one of the deepest and most beautiful open questions in all of human knowledge. But science has done something remarkable. It has shown us that time is stranger and more wonderful than Newton imagined, that it bends, that it flows at different rates in different conditions, that the universe we live in contains within its mathematical structure the seeds of possibilities that would have seemed like pure fantasy to every generation before the 20th century. We know that time travel to the future is real, confirmed, used in technology every day, We know that the universe does not obviously forbid the rest. And we know that time itself, this most intimate and immediate feature of human experience, is something we do not yet fully understand. Perhaps that is the most extraordinary thing of all. The thing you feel most directly, most constantly, most inescapably, every second of every day is still a mystery. Time is passing right now, and nobody fully knows what that means. Let that thought carry you gently into the dark. The mystery of time is not a problem to be solved tonight. It is a wonder to be felt, and you are feeling it right now in the most direct way possible, by simply being here. Sleep well.